All right, and as we continue on here with another part of this critical values thing, you can find the absolute extrema on a closed interval. So, in order to find the extrema of a continuous function on a closed interval from a to b, we are going to follow these steps. The first of which is you find the critical values of f on that interval from a to b. So we did that in the previous video. We found the critical values by setting the derivative equal to 0 and also determining where the derivative was not defined. And once we had that information, we were able to go forward and do something good with it. Then the next thing that we did after that, or should do after that, is evaluate f at each critical number in our interval from a to b. And then once that's done, we're going to evaluate at each endpoint of a to b. So we're going to find f of a and f of b. And once we discover what all of these things are, then the least of these values is the minimum, and the greatest of these is obviously the maximum. So this is the process that we're going to use for finding the critical values. Let's jump in with a couple of examples here and show you how this works. So first of all, we've got this function 3x to the fourth minus 4x third on this interval from -1 to 2. So let's jump in and find the critical values first, and that involves finding the derivative, which winds up being 12x to the third minus 12x squared. And if I set that equal to 0 and I factor out a 12x squared, then the critical values are going to be pretty easy to find out. This is going to happen when x is 0 or when x is 1. Okay, so we've got those, and we need to find what f of 0 is, and we need to find what f of 1 is. So the big thing that you need to remember is that you put this into your original f of x, not the derivative. Because again, we're trying to find the maximum and minimum values of f of x, so the derivative doesn't matter here. It's the original function that we care about. And finding those out is going to be pretty easy. If we drop those into our original function, I think you're going to get a little bit of no surprise there that f of 0 is 0. And when you put 3 times 1 to the fourth minus 4 times 1 cubed, you're going to end up with -1. Okay, now that doesn't guarantee that that's the maximum and minimum value, because you also have to consider the endpoints as well. So as we go to do that, I need to find what f of 2 is, and I also need to find what f of -1 is as well. So as I go to find what f of -1 is, I'm going to end up getting 7 over here. So you can see that that's already the leader in the clubhouse as far as max values go. And then when we go to find out what f of 2 is, okay, well, 2 to the fourth is 16, and 3 times 16 is 48. And then 2 cubed is 8, and 8 times 4 is 32. So you're going to wind up getting a y value of 16. So now we know the truth. Now we know that this produces the maximum and this produces the minimum, because those are the largest x and y values. Okay, now the critical number x equals 0 doesn't yield a minimum or maximum. So that tells you that the converse that we have here isn't necessarily true. I mean, we're not going to get guaranteed that just because a derivative is 0 does not guarantee that that particular point is a local min or local max or even global, depending upon the circumstances. All right, let's take a look at something maybe a little bit more challenging here. F of x is equal to x to the 2/3. Well, if I go to find f prime of x, I'm going to get 2/3 x to the negative 1/3, which when I rewrite it looks a little something like this. And there's no place where this derivative goes to 0, but there is a value for which it becomes undefined. And that, of course, happens at x is equal to 0. So I need to find what f of 0 is, and lucky for me, 0 raised to the 2/3 power is indeed 0. But I also need to consider the endpoints. I need to find f of negative 2, which is going to be negative 2 to the 2/3 power. And I also need to find f of 3, which is going to be 3 to the 2/3 power. Okay, so I'm going to reach for my calculator on this one and see if I can find out what the approximate value is. And if I punch this one in for f of negative 2, I'm going to wind up getting 1.587. And if I take 3 to the 2/3 power and try to figure out what that is in my calculator, I'm going to end up getting approximately 2.080 when I round to 3 places. So I have now what my max is that occurs at x is equal to 3, and then there's my minimum when x is equal to 0. So again, not terribly surprised by that once we punch it into the original function. Okay, now functions in Extrema can occur only at critical points and endpoints, but remember, not every critical point signals an extreme value. Think about x cubed. I mean, you figure that one out for yourself, and you're going to be like, oh yeah, I guess that's not a min or a max. You might have to look at the graph to do it, but it's not so bad. Okay, now speaking of looking at the graph, I've taken the liberty of giving you the graph here from Desmos on this particular function. And we can find the extreme values of this. Now, if you remember, taking the derivative of a piecewise function isn't so bad to do. It's just the derivative of each piece. So when x is greater than 1, the derivative is just 1. And when x is less than or equal to 1, the derivative is going to be negative 4x. So we can tell that there's going to be a lack of differentiability at x is equal to 1. And when we take a look at the graph, that kind of bears out the case because we've got this sort of hybrid sharp corner / cusp at x is equal to 1. But there's also another critical value too. And that critical value occurs when x is 0. Because 0 is less than 1. And when we are left of 1, we obey the rule negative 4x on our derivative. Then the derivative at 0 should be 0. And once again, we're kind of confirming this by looking at the graph and noticing that there is a local max at the point 0.5. So that's where we have our local max and local min. But keep in mind, these aren't global because I don't have a closed interval. That's going to be a key detail as you work through these problems. Very good. Enjoy.